Oh, hey, cool kids. Today we're going to learn about acceleration. Follow me. Up until now, we learned about constant velocity. That is when an object moves in a direction and that doesn't change. Acceleration happens anytime that velocity changes, whether it's direction or the velocity itself. So, for example, if I turn here and I stop, at that instant, there were two instances of acceleration. The first instance of acceleration was when I turned, because I changed my direction, changed my velocity. Second instance was when I changed my speed, when I came to a stop. The first example of acceleration that we're going to go over is any object that has a positive velocity with a positive acceleration. Now, when that happens, the object speeds up, like this. And the second example of acceleration is when I have a positive velocity, but there's a negative acceleration. And when that happens, I slow down, and eventually I come to a stop, like this. Now let's take a look at how we can explain acceleration using the dot model. So up until now, we worked with the constant velocity model, and it'll look something like this. If this yellow dot is our object, and this green vector is our velocity vector, we know that the object, if it has a constant velocity, will have a constant change in position over a constant interval of time, right? That's the definition of velocity. Now let's take a look at how we can explain acceleration using the dot model. So up until now, we worked with the constant velocity model, and it'll look something like this. If this yellow dot is our object, and this green vector is our velocity vector, we know that the object, if it has a constant velocity, so let's take a look at this model. We have an object that undergoes a acceleration. Now, if that object has a acceleration, after a certain amount of time, it'll have that velocity. So it will end up in that spot. Now, at that moment, this object has this velocity, but it is also undergoing a acceleration. So upon this position, this object will have this velocity plus this acceleration, like so. You see how it lines up? Now, in the next interval of time, we will know that the object will be right there. It'll have this acceleration, and before it had this velocity. So it'll have a brand new velocity, which means that it'll end up right there. So if we take a look at it and remove all the velocity and acceleration vectors, we can see how the object incrementally or exponentially gets further and further away.
All right, so we've seen a couple of examples of acceleration. So let's do a wrap up. The definition of acceleration is a vector quantity. Now remember, vector is anything with a magnitude, which is the number, and the direction. And the direction can either be like north, south, east, west, left, right. But more commonly, we'll use positives and negatives. Okay, and usually anything that's going up or to the right will be considered to be positive. Anything going down and to the left will be considered negative. Right? So acceleration is a vector quantity that's defined as the rate at which an object changes its velocity. An object is accelerating if it is changing its velocity. That's the definition. Now, it's very important to know that if an object is accelerating, it does not mean that it is going fast. And you'll hear laymen often use this when they speak. For example, in sports, you'll hear that the announcers will say that an object is accelerating when they really mean that the object or the runner or the racer is going super fast. Okay, now I'm going to show you the different models that we will use for acceleration. This is the numerical model for constant acceleration. On the left-hand side of the column, you can see that I have time, and on the right-hand side, I have the velocity. In this case, this object is accelerating at 4 meters per second per second. And some of you might be more used to calling acceleration 4 meters per second squared, and that's where the per second comes from. Now, when we first start acceleration, I like to refer to it as meters per second because we're used to the idea of velocity having the units of meters per second. So what that means for us is that for every second, there is an additional velocity, meters per second, velocity per second. Okay, so for every second or unit of time, the velocity is changing. So in this case, the acceleration is going to be 4. Initially, the velocity was 0, but because there was constant acceleration, that 0 meters per second will change by 4 meters per second every second. See what I mean? So it'll go from 0 meters per second to 4 meters per second. And after 4 meters per second, during the next time interval, it will change by another 4 meters per second. So it'll go from 4 meters per second to 8 meters per second. And after that, it'll change by another 4 meters per second. So it'll go from 8 meters per second to 12 meters per second, and then 16 meters per second. So you can see how it is changing the velocity of the object. All right. Now, by definition, you do not need to have constant acceleration, although that will be what we'll be using throughout most of the year. And object can be accelerating at a non-constant rate. So this happens when an object changes its direction, when an object goes, let's say, north to maybe northwest, or if you are in your car and you turn your steering wheel, by definition, you are accelerating because you are changing your direction. Okay? Or any time an object makes a change in its velocity. Now, the equation model, this is what we get. Acceleration is equal to delta v, or the change in velocity over time. Okay? Acceleration is the change in velocity per unit of time. And this is what the graphical model looks like. So here we have a position versus time graph. Okay? Up until this point, we were used to a linear line for a position versus time graph, and that's because we had a constant velocity object. But now, because the object is accelerating, it no longer has constant velocity. Rather, it has this exponential curve. Okay, so whenever you see a curved line for a position versus time graph, you know that the object is accelerating. And here we have a velocity versus time graph. Now remember, by definition, acceleration is when an object has a change in velocity. So in this case, that change is constant. This object's velocity is constantly changing, and we know that because of the slope. The slope is linear. It is constantly changing. Okay, and if we were to find the value of the slope, we could see what the acceleration is. And last but not least, we have the acceleration versus time graph. And from here, we can see that the object has a constant acceleration. Okay, there's no slope. It's a flat line. There is no slope for acceleration versus time graph for a object with constant acceleration. So all three of these graphs describe an object that is going under constant acceleration. And by the end of the unit, you should be able to go from one graph to another, and back and forth. The other way of knowing if an object is accelerating is using the dot model. And this might be a model that we're more used to. Okay? So in this scenario A, we see that the object is speeding up. The dots, they were closer together, but you can see that they're getting further and further apart. And that's because the velocity is increasing at a constant rate. It's getting faster and faster. B is the reverse of it. It's an object that was going fast, and we can tell that because the distance apart between the two dots is further apart, but then it slows down. The dots get closer and closer together. All right, now let's fire off some questions. Okay, these are some questions that I normally get. If an object has a negative acceleration, is it slowing down? Now, this is a very common question, and it is often a common mistake that students make. Just because something has a negative acceleration, it does not mean that it is slowing down. And here's why. So, for example, let's say we have an object, in this case a blue ball, and it is moving with a negative velocity, so to the left, and it also has a negative acceleration. Okay, so you see how we have two vector signs that match up, negative and negative. In that case, because the signs match up, the object will not be slowing down. In fact, it'll be speeding up. Now let's take a look here. This green arrow represents the acceleration, and this gray arrow represents the velocity. So, just like in the beginning of the video, if we add the two vectors together, we get this new velocity, this red arrow. And this red arrow is greater than this gray arrow, which was the old velocity, or initial velocity. And this red arrow is the final velocity, right? And so after 1 second, this object, it was going at negative 8 meters per second. But because it was constantly accelerating at negative 1 meters per second, it is now going at negative 9 meters per second. So it sped up. Now with that question, I usually get the next question. If an object has a positive acceleration, can it get slower? All right, so here in this picture, we have an object with a positive acceleration in red. It's pointing to the right, it's positive, but this object has a negative velocity. So in this case, the velocity is negative, yet the acceleration is positive. Normally, we associate positive with things that maybe speed up or increase, but not in this case. Because the velocity has a negative sign and the acceleration has a positive sign, they go against each other. And when things go against each other, it shrinks down. So in this case, the object had a velocity of negative 8 meters per second, but then accelerated with positive 1 meters per second. And so after 1 second, you can see the new velocity in green. It is negative 7 meters per second after 1 second. And that's all we have for today. I'll catch you next time with a new video. Bye-bye.